Alright, we're going to deal with sections 5 and 6 in this video. Section 5 deals with the detection of radioactivity. And there are a few different ways that people commonly detect radioactivity. And the first one is by the use of a film badge. Okay, film badges record the extent to which different workers are exposed to radiation. This radiation that interacts with some kind of like photographic piece of film, usually underneath their name tag, and then that'll kind of tell them exactly how much radiation that particular worker has been exposed to, and whether it's too high of a level or whether they're good. Usually for workers like x-ray techs and things of that nature have those film badges. Alright, the next thing here would be the Geiger counter. Okay, Geiger counters measure radioactivity that come into contact with an anode, connected to some kind of voltage source. They will then amplify and then create some kind of audible like blip. Alright, these are usually have two pieces. They're usually the voltage source with like a handle on it, and then they have usually another little end that you kind of wave around and point to whatever you think or wherever you think the radioactivity is actually located. There are some other ones that are all one and combined, but there are a lot of the old school ones that are a little more like two pieces. So that's a Geiger counter. You also then have what we call phosphors. Phosphors are where different substances will give off light when in contact with a radioactive source. So if I come in contact with some sort of radioactivity that I'm not supposed to, it will turn blue. If this turns red, or gives a certain bright pink light or bright yellow light or something when it comes into some kind of contact with radioactivity that I do not want to have. That's a phosphor. And then the last one are radiotracers, and these ones are very common in the medical field. A radiotracer will just trace the path of that element that's radioactive. I gave an example of like cobalt-60. I believe that is one that they use for like tracking through x-rays. There are a couple other also ones they use to track through, to kind of see your intestines or to see different blood vessels or arteries or things like that in the medical field. Right now, really, energy changes associated with nuclear reactions, and energies associated with a nuclear reaction can be considered using E equals mc squared. Okay, there are small changes in mass involving some larger change in energy, and these large changes in mass are much more than actual normal chemical reactions. So we're going to look at some problems when dealing with these energy changes in nuclear reaction. And the first one we're going to look at in this nuclear reaction is dealing with how much energy is lost or gained when a mole of cobalt-60 undergoes beta decay, and they give you the reaction, the mass of cobalt-60 atom, and they give you the mass, and the mass of the nickel-60 atom is there, and they give you the mass. Notice how they're really not that much different. But the first thing you got to look at now is how exactly much energy we have lost, which is the E. Well, I have the E part, I need the mc squared part. So the C is the speed of light, so that's a constant, so we're good there. The E is what I'm looking for, which means I should be able to figure out my mass from whatever they give me. Why am I change in my mass? Well, when they give me the mass of the atoms, these masses include protons, they include neutrons, and they include electrons. It's the mass of the atom. Okay? But what you want to do is kind of get rid of the actual electrons and leave behind the protons and the neutrons, because that's what we're dealing with when we have the energy change. So that is what we are doing right here. Okay? I take my 59.933819 AMUs, I subtract 27 because there's 27, and then this right here, okay, this 5.4858 times 10 to the negative fourth, that is the mass of my electron, because I want just the mass of my nuclei that I'm looking at here for the energy, because that's what's going on with my reaction, is we're trying to deal with the nucleus. Okay, so the same thing for, because that's cobalt-60, the same thing for my nickel atom. Take my 59.930788, okay, minus the 28 times 5.4858 times 10 to the negative fourth. That's my electrons that I'm getting rid of. Nickel has another electron to get this mass. Well, when I look at my reaction, okay, I'm going to take my products minus my reactants and figure out how much mass was lost there. So these are my products. This is my reactant. So I'm going to take products minus reactants. I take my nickel-60 plus the electron, okay, minus my cobalt, which is my reactant, and I should get my mass here of 0.00303830 AMUs. That's my change in mass. I just plug the mass into E equals mc squared, and I'm going to get 2.72 times 10 to the 11th joules. That is how much energy I will get out with this reaction. Okay, nuclear binding energies are dealing with things being bound together, okay, obviously by the name. The masses of nuclei are always less than the masses of the individual nucleons of which they are composed. So the individual parts weigh more than the actual nuclei together. Okay, the difference between the nucleus and the different parts when we add them together is called a mass defect. It's kind of the defect or the difference. Okay, the energy is needed to break apart the protons and the neutrons, and that's where we get kind of the difference in mass, because we have some energy that needs to go in to kind of break them apart. If you have to put energy in and you get energy out of something, there's going to be a change in mass there, because energy and mass are proportional based on E equals mc squared. This energy that's needed to separate the nucleus into its nucleons or its parts is called the nuclear binding energy. Okay. Nuclei with intermediate mass numbers are more tightly bound and more stable than those that have smaller mass numbers or larger mass numbers. They have a higher binding energy to kind of a certain point, and we're going to look at a chart here in a second where there's kind of like a high binding energy is good, but not always great. All right. A higher nuclei will tend to gain stability by fission. A lower nuclei will tend to gain stability by fusion. Okay, so if I look at this bottom chart here, it's kind of the certain point thing that I'm talking about, all right? I have this iron, okay? Iron is actually our most stable element here, or iron 56, okay? These are my heavier mass numbers with the protons with the neutrons, okay? They will go through fission to become more stable, whereas the lighter mass numbers will go through fusion to become more stable. All right, but I have my binding energy per nucleon, which just means per each particle. Okay, so see how it gets higher, but these really aren't as stable as this one. But these are higher too, but they aren't kind of as stable as this one. So a higher binding energy does not necessarily mean that it is stable. It's kind of more with the mass number. Okay. And that has to do with kind of how much mass defect you have there as well as to what is kind of the most stable. So we're going to look at a problem here. Okay, so the mass of my helium, or helium-4, okay, nucleus, by experimentation is 4.00150 AMUs. Somebody found that by experiment. But what I do know is that a proton mass is 1.00728 AMUs, and a neutron mass is 1.00866 AMUs. So that means, okay, that an He4 should weigh 2 times the 1.00728 plus 2 times the 1.00866, which is going to be 4.03188 AMUs. So that's not the same thing. The parts do not seem to add up to what I see it being. And that is our mass defect, our mass difference. Okay, so 4.03188 minus 4.00150 is 0.030 AMUs. That is my mass defect. This mass defect is accompanied by some kind of energy change, because I had to put energy in to kind of put these particles together or get these particles apart. So I'm going to try and break apart these particles. I have to also change the mass, which is where we get the E equals mc squared. I have the E equals my mass, which is 0.03038 times the speed of light, which is 2.99 or 3 times 10 to the 8th meters per second. And it is squared. Then my E value is 4.53 times 10 to the negative 12 joules. If I were to figure out it per nucleon, I would have to divide by 4, because I'm going to divide by the total number of nucleons. And those numbers are in that chart that you see there. Okay? You have to be careful with the joule number, and I actually need to put this in there. That's partially my bad right here. This will not give you this number. I have to change this AMU into kilograms, because kilograms are what go along with joules. So I actually have to take that 0.03038 and divide by 6.02 times 10 to the 23rd, because that's actually how many AMUs are in 1 gram. Then I again have to divide by 1,000 because that's how many grams are in 1 kilogram. And I need to really be in kilograms to deal with joules. Kilograms times a meter per second squared, that is a joule. So that's my bad there. You got to add that part in there as well to change your masses.